Hey everyone, this is part two of the three-part series of doing audio classification with Pytorch. Whether you're a musician curious about the technology or just someone interested in how computers understand music, hopefully you'll learn something valuable from this. The first video was mostly concerned with the concepts, so definitely check that out if you want to follow along with this one, because this time we're actually going to be building a whole music genre classifier, and with the deep learning concepts out of the way, we'll mostly be digging into the nitty-gritty of using Pytorch. This example will use a CSV dataset, but stay tuned for video 3. In the last one, we will work with raw audio. So what we're going to do here, this time we're going to use an existing dataset instead of making like a really dumb like toy mathematical dataset, which means we get to use a fancier neural network. Let's go ahead and do like the install because I need to do that and go ahead and do the imports. So Kaggle, I'm actually curious. Do you know what Kaggle is?
I do. Basically, I know that it's a place you can find data sets.
Yeah, and there's like little competitions and stuff. Like the datasets are publicly available, and then a lot of people will upload their notebooks about how they solved the problem for that dataset, and it's actually a really cool place to learn. Uh, if you ever if this is like to the audience of the video, if you're curious to actually try more of these and to learn more, or you think my explanations are terrible and you wish for like better annotated like notebooks, if this is like enough of an introduction to get you interested in trying it, like go to Kaggle and like look at people's example notebooks, look up a data set that solves like the type of problem you might want to mess with or play with yourself, and see what they do. It's really good opportunity to learn. So uh this part, because I'm like just gonna download the uh Kaggle dataset, I need to grab my token, and I might cut this part real quick so you don't see my token. So now that I have the Kaggle token, and again, I could technically I could download this dataset onto my local computer and then upload the whole thing, but this is a little bit more efficient for me, and this way anybody can run the notebook without issue. And if you want, this is actually really important, I think, it shows you the URL. So it's just like kaggle.com/datasets plus the name of the dataset you want to grab. And you can take a look at this dataset here. You can look at the details. So the problem we're going to be solving, let's actually just go ahead and read. So we have a bunch of genres. It's a collection of 10 genres with 100 files each, which is awesome. A nice split of the dataset. There's 30 seconds in these that it's taking information from. So I should say this is a CSV file we're going to be reading from this time. It also comes with audio files, but for this example, I'm going to be reading from the CSV. And the information in the CSV file, we'll get actually as we get through the notebook, we'll see exactly how that works. So there's two versions of this, and it's really awesome. You can see some stats about just the distribution of each feature as you go along. I need to unzip it, which also takes a minute because you can only upload like one file. It gives you like a zip file, and then it needs to unzip the zip folder. So we're gonna let this run, and then we're gonna use you can see both of the CSV files over here. We're just gonna use the 3-second CSV file because it also feels a little bit more impressive that we don't need to look at a lot of information to make a prediction here for our classes. And then df.head is just PD. Also, I should mention pandas is for like all kinds of data analysis. And what I'm recently like really understanding and appreciating is it's more of like we see things in rows, but things are more like columnar because we like to do analysis of data just like where we see each feature on its own. So that's how almost like if you see like the data distribution of these, I forgot which tab that was in. But if you see like the data distribution of each feature and stuff, that's easier to calculate if we just grab like a column at once. And pandas is just like a really awesome way to work with data in Python. So you can see all the features that's picked out here. I can't like describe in detail what each one is. Just something to know. Actually, so Gage is also a bit of a musician. Let's talk about the ones we do know. We'll gloss over the ones we don't know. Just know it's just a lot of features. So like RMS is basically like the average value of the waveform. not, I can't, we're not going to say it's loudness, but you can think of it roughly as like the average loudness. It's not um the spectral centroid mean. It's all the spectral stuff is basically like if we did an FFT and we got what you'd see like on a graphical EQ, and maybe I'll probably like pull up a because it looks like another waveform. uh I'll probably pull up like a graphical picture of a graphical EQ or whatever. So if you did that FFT, it's like the spectral information tells us like what's going on in each frequency band, which frequency band is most pronounced, where are there resonances, where are there other factors like that. MFCC is like the most, I think, really gives you the most information at once. I do you feel like going into a little bit of a technical audio talk, Gage? It's actually up to you.
Sure. I'm interested.
Yeah, so uh, there's like regular spectrograms, and I might have to like edit this to show pictures. There's like regular spectrograms where we have like x-axis is time, y-axis is frequency, and then the colors tell you like the magnitude of each frequency. And then the Mel spectrogram is basically one that's balanced for like the way humans experience audio. So our resolution of hearing isn't the same at all frequencies. And basically what like I think most people watching this video, like my YouTube channel's audio, probably already know like the Fletcher Munson curve or whatever. And then the Mel frequency, the spectrogram basically like balances it to closer to like a meaningful split of the frequencies instead of a linear thing. And then the Mel frequency spectral coefficients gets like way more mathematical. But from my very vague like understanding of it, you could look it up. Don't like quote me on it, but it's like an FFT of the FFT, which takes very like general features of, again, like if let's say this is a frequency graph, right? So I have this is a lot of resonance over there. So like this is like 20 hertz, and this is like say like 1k hertz, and then like up to 20k hertz or whatever. Basically, it picks up if you do like an FFT of this, then you basically see where there's pronounced features, and then as the spectral coefficients get higher and higher, it attends to more and more like fine gradations in that waveform. But it's not the waveform. This is like the spectrum. This is the like frequency analyzer that we're doing an FFT of. It's kind of wild. But basically, you know that it gives you a ton of information that's much closer to human perception of audio than what you would usually get from like a more linear spectrogram. Yeah, and then there's different things about the mean and the variation it looks like for all of these, or variance. I don't know. All of these features you could pick up using. There's a couple of audio libraries that I think Torch provides one. There's torch.audio. There's like torch.audio. There's Librosa. I think Librosa is a really good one for most of the stuff. And I think there's one more I've used before. Can't recall off the top of my head. But you could, to generate this CSV file, take literally just like a raw audio wave form, and then use the Librosa library. It's like Librosa.mel spectrogram of this audio file, right? And then it would spit out these values, and then you'd have to collect them for a ton of files and put them into a nice format like this. But the person who made this data set already took care of that for us, which is very nice. So again, in our next notebook, we're gonna actually be working with like from the raw waveform, but in this example, we're just using a nice CSV file, so we can get a little bit more comfortable with how we'd interact with these like problem data sets in Pytorch. Cool. Makes sense? I kind of ranted there, but
No, that makes sense.
Cool. All right. So this is now I have my data frame, which is just like literally just like putting the CSV file into a format that's Panda format. So this allows me to like go through the columns really easily. So I can look at the labels, and I'm going to see how many of each label is inside that column. So we have the different genres on the left. This is our label, and then we have about 1,000 of each of these. I think what probably happened, most people have like different versions of their data sets, and it got cleaned a little bit. So disco and classical and country lost a few songs, which might have been like they're either misclassified or just files with errors in them for whatever reason. So still a really good, really good distribution of data. We like to have more or less close to the same amount for each class. Otherwise, like if it sees one example of like a cat and it sees 1,000 examples of a dog, it's obviously just gonna predict that everything's a dog because that's what the data basically says. And it doesn't learn enough about what features dogs have. But we have a good data set here. I'm gonna go ahead and change these labels. Obviously, we can't do math when we come to like even on classification. We can't do math on strings. So we have to turn all of our categorical data into numerical data. At least the categorical data that we're using, right? So this is just me finding like it's the list of the unique labels we have, which is again just like this list right here. And then for each one, for each value here, it just changes it to the index in that list. This is like a little shortcut. You know Python, and this isn't the point of the video, so I'm not going to go into detail on that. Let's go into the train test split, which we already talked about before. Random state, this is like a seed. It's just so that every time this notebook is run, you're going to have the exact same results. So nothing important here. This is just me seeing the data distribution when we do the train test split. This is why it is so nice to use. Not only is it one line to split your data set into train and test, but it also leaves like about the same distribution, right? So it's mostly these like top 5 classes, and then for the last ones, there's just a few less, right? And it's a really nice split of 0.8 for train and 0.2 for test. I don't know why I chose to put 0.8 for train instead of 0.2, but whatever. Same output. Something super important. I'm actually gonna show you. Why not? I'm gonna show you what happens when you don't normalize your data first. So when we do calculations and we're doing like all the calculus to decide how much each feature contributed to the final output, if we start with very large values, they're obviously like mathematically going to seem like they matter more. So normalizing the data keeps things within, I'm assuming standard scalar is mean of 0 and standard deviation of 1, and that keeps it from just like the raw like size of the initial integer from contributing too much to how much the network thinks it contributes to the answer. So everything's scaled. I don't know a nicer way to put that. So we have our labels. Now we have our data sets. We make the loaders for each data set. This, I don't know why it's 8. I can make it 32. I can make it anything because again, like when we do batches for training, it actually does change how it calculates because it only does back propagation once for each batch. It means it's like kind of like learns like the general pattern between all of them more instead of adjusting for each specific example. Batch size and training data set, train loader matters. Batch size and test, I don't think there's no reason for it to matter. I'm just going to bring it up to 32. Not sure why it wasn't before. Cool. And then this is our neural network, just like before. This is just so we know we don't know what the input size is because all we did is we took this CSV file, we took away like the categorical things and the like length. We didn't care about that value. It doesn't change the output. We just took some columns out. We don't know how many columns we have left. So this is just our way of saying is like however many features come in from the CSV file once we drop the file name, length, and label column. And then, of course, the label column is what we use to make our labels, which we will use in the training loop. So again, just finding our shape. We start with a batch norm, which again, it's like the normalization we do here of making sure that none of the values are disproportionately large and contribute to our final output when really they might like just because this column has, in general, larger values. We don't want that to contribute much. So is that making sense, or should I give an example? I'm gonna give an example actually.
Yeah. Okay.
Sorry, just in case. So like, let's say one of our columns is like it's something like monetary, and let's say one of our columns is like time, let's say years in the bank, right? So if there's like years in the bank, years, all the values are going to be like 2 or like 5 or maybe like 20 at the largest. But if we say like one of the columns is like amount in the bank, and like somebody has like $1 million in the bank, and maybe this is all like companies, and then there's like extremely large numbers in here, right? All these are gonna like by necessity look like they're contributing a lot to the value, even though like from one to another, like this might be like 0.05 of what somebody else has, you know. So all these features are scaled so that they don't contribute like, or mathematically seem to contribute too much. Is that making sense? I just need an example for when I say stuff. Cool. Oh, this is one of my, okay. So we have our linear layers, we have our activation function, and we have our dropout. And again, like these layers are kind of just like guess and check. This wasn't a very difficult problem, so I didn't think too hard. There's not like a big explanation about why I chose this number of layers or these particular numbers. But I should talk about what dropout is. So if we again make it into a classification problem, let's say, yeah, let's go back to our fruit example, right? And we have a few features here. Then we have a few classes it could be, right? Let's say that this one right here is, why not? Why not? So it's back to the color. So this is again the purpliness of this feature attends to the purpliness of the image. And again, I should say like these features never end up like quite so clean. Like if we took this value and somehow graphed it so we could see like the output, if this value was small and then large, it won't attend specifically to purpleness. Like these features are very abstract, and that's like how the network learns. So it's not like it's actually the feature of is it purple or hey does it have pause. It's very abstract features that may or may not more or less correlate to things like how purple it is. So disclaimer there. So let's say that this is how purple it is, and I am trying to categorize. Yeah, I'm categorizing fruit again, right? One of my classes is a grape. One of my classes is a pomegranate. That is a fruit, right? One of my classes is an apple. One of my classes is an orange, right? And let's say, because of my examples, as the network learns, it sees, hey, anytime this is activated, anytime that it seems like it's purple, it's a grape. And then it sees a lot more examples. Maybe sometimes it's a pomegranate, but it sees, hey, every time it's purple, it's a grape. And then maybe we have some other classes that are also purple. Name another purple fruit. I'm at a loss here.
I'm thinking. Can't really.
Yeah. Sorry for the pop quiz there. So let's say we have some other fruit that are also purple. But every time it sees purple, it's convinced if it's purple, it has to be a grape. Or let's say I'm categorizing animals, and I said, yeah, we're playing I Spy with my little eye, an animal that has black and white patterns on it, and you're like, oh, it's black and white. It is definitely a cow. And then maybe I ask you this question 100 times, and it's always a cow. And then maybe I have a couple examples of like it's a Dalmatian or it's a zebra. But because you saw so many examples, you're certain if it has this pattern, if it has this feature, it is definitely a cow. One things to normalize this, or what is it, regularize, I should say, is what we call a dropout. So if with a dropout of 0.4, if I have 4 features, every time, if the model is training, every time it goes through a forward pass, one of these nodes is just ignored. So if I have to look at all the other features, like I might have told it like, hey, it weighs like 500, or how much does a cow weigh? it weighs like a ton, right? And it moves, but you saw the feature of it has black and white stripes. So you said it was well, it's a Dalmatian or something. Let's say it's a Dalmatian. It doesn't weigh 500 pounds, but you saw this one feature and you always think that it's a cow. So when dropout happens and I just remove the feature of it being black and white, then the network has to learn, well, if it weighs that much, it's not a Dalmatian. Maybe it's a cow. Maybe it's something else, but it just loses information about this one node each time. And again, like it'll be randomized to 0.4%. So if there's 4 nodes, then every time there's a forward pass, one of the nodes is ignored. So maybe the next time it ignores the weight of the animal, and the next time it'll ignore like the the sound it makes. Right, it'll ignore the fact that it moves. Right, probably not the best example, but you get the idea. Every time it runs through, one of the features is ignored, or however whatever percent is ignored, and that prevents it from attending too much to one feature by default. Cool. That's the only new layer in here, actually, besides the batch norm, which is just normalizes across the batch. So 32 examples. Across those 32 examples, the values are normalized. So one example doesn't seem like it has values that are like obnoxiously bigger than the others. Yeah. We can print our model just like before, and it just shows us the thing that we just made. Yeah. And then training loop, like I said before, like it looks almost exactly the same. This time the test accuracy is actually going to be valid information for us because it is a prediction problem. So again, I should say, like, if we have an output layer, this is a classification problem, right? So some information goes to however many classes we have. I think we have 10 classes, right? We have blues or whatever. So we'll see. Yeah, blues, jazz, and all those. Let's go ahead and see. Yeah, we have 10 classes, and we know that because that's what our output layer says. We have 10 classes, and for each of these classes, what it's really doing, especially when it goes into the, you can, okay, small detail. You can put a softmax here, like, so now it's a probability distribution like we talked about earlier, but internally the cross entropy loss, which is just like the loss you use when you have multiple classes, internally it does a softmax on its own, so it's just redundant, but you can do that. So there is a softmax applied to all of these, and we'll say that there's like a 0.5 chance of this, and like 0.1 or 0.07 or blah blah blah, that adds up to 1. It just calculates how wrong it is based on the number of classes. It's like some factor of the number of classes. And then it also, what's really important about it, it's not just like every time it guesses, it's like 1 out of 10. It's based on how confident it was. So we're rating it not only on what class is the highest probability. Oh, that's what okay, so the torch.max, right? This is why we have to do this for guessing our evaluation, because we have to choose the highest class. But when we do this in the training loop, there's no torch.max here, because it needs to know what probabilities it got for across all of the classes, right? So we're grading it not only on did it get the right class correct, did it do the right classification, but how confident was it when it guessed, right? So if I said, like, if the answer was let's say the answer it guessed was giraffe, but we're actually supposed to be guessing fruit, like that's a lot different than like getting like an orange or an apple wrong. It's a lot different from, let's say, super high confidence on giraffe isn't the same as like, oh, I thought, maybe there's like a little bit of a chance of it being a giraffe. It's not super wrong. It probably should be completely 0, but we're not going to grade it harshly. But if it says, yeah, this is definitely a giraffe, there's no chance that this is an orange, even though the picture was an orange, then yes, this is very wrong, and we need to like show that in the loss function, is what I'm trying to explain. Make sense?
Yeah. Okay,
cool. And then the rest of the training loop is exactly like we talked about before. There's some like other parameters inside the optimizer we can do. There's no reason for the scheduler here. I'm not sure why that's there actually. And then we can run it. Well, and I think, yeah, relatively slower. See the loss go down slowly. And we can also check the test accuracy now. So as the loss goes down, we'd expect the accuracy to go up. That's not necessarily the case, especially since, remember, the test data is different from the training data. So what happens if your like training loss goes down to like absolute 0, but your test accuracy is poor? It means that it overfit to the data, which is just our term for saying like it basically just memorized the input, right? And it just it memorized the answers on the review sheet, and then when it went to the test, any question that looked the same, it just put in the exact same answer. It's not learning the patterns, it's just memorizing what it saw when it was studying, per se. I don't think we need to wait for it to finish, because I remember this one, like the best it can do is like 95%, because some of the examples are like, we have, if we look at our genres over here, we have blues, what is it? Blues and rock and country, and then there's like country blues and there's like country rock, like they're overlapping overlapping genres.
Yeah.
This is actually about as accurate as it can be. This is about as accurate as a human being can be on the test data. So we'll stop it there. We can see pretty good accuracy, like 95%. Training loss goes down sometimes. I mean, like if it perfectly fits, then sometimes it'll go down all the way to like 0.000. In this case, this is as good as we can get, but we can see it doing its thing. Any questions left for this notebook?
No, I think that makes sense.